Good evening, everyone. My name is Jyoti Sharma, and this is week 3, and the session is from 6 to 8 p.m. This is my brief introduction that I'm right now a PhD student in ICER Bhopal, and right now I'm a currently PMRF research fellow. This is as obviously what we did in last 2 week that how we will proceed. So this is like I have a lot of MCQ questions, and you people are encouraged to write in the chat box whatever the answer you think right, and then even if it is wrong, just don't worry because I'm here to correct you. Okay, so first we started with week 1, and because right now the week 3, but I'm giving you the brief discussion what we did actually in week 1 and week 2. So just one or two slide over this week 1 and week 2 content. So first we started with the introduction, and in introduction we started how we have a source. From source, the contaminant can go to the environment, or you can say to the environment compartment, and then how it can be taken by the receptor, and here the receptor is nothing but the human being, right? Then we went to chemical of concern. So we have a lot of chemical, for example, mercury, arsenic, and antimony. So we have a lot of chemical, and we need to understand the physical and chemical property of that particular chemical, and how it is moving from one compartment to another compartment, and so on. So we tried to discuss that briefly in this lecture too. Then we came to uh, water quality and screening parameter. So we learned that we have different parameter by which we can check the water quality. For example, it is a turbidity, or it is the taste, or it is the color, these are normal physical characteristic of the physical parameter for to check the water quality. But along with that, we also checked the biological parameter to check the air quality, for example, BOD, COD, theoretical oxygen demand, and so on. Then we went to air quality parameters, and we talked about different type of contaminants we may have in the atmosphere, and one very prominent pollutant that we have in air is particulate matter. And we talked about how we can measure the settling velocity of particulate matter using Stokes law, and we calculated that settling velocity also. So this is what we learned in week 1. And then we discussed in week 2 about the physical chemical property of interest. Either it is organic in nature, it is inorganic in nature, it is polar or non-polar, it is then hydrophobic or hydrophilic in nature, so that uh, we can from that physical and chemical property of our contaminant, we can decide, or we can get to know where this pollutant will go to. So for example, if it is a hydrophobic, then we can say that barely it can present in water, right? It will be either in air or in the soil, so something like that. So we can based on the physical and chemical property of the contaminant, we can say something about where it will be present now, right? Then we talked about the partition constant, and I think that was what we learned in week 2. But we are yet to have some question on soil air partition coefficient. We started it, but we couldn't complete it. So yeah, so we will complete it right now. And application example of equilibrium partition. So we will see these lecture 7 and 8 right now. And along with that, I also have week 3 syllabus, that is introduction to environmental monitoring and sampling. Why do we do the sampling? Why do we do the monitoring? What are the objective? What are different questions that we try to we try to solve? And then how we can check whatever analysis we are doing, what kind of quality we are having of that particular environmental analysis. So do we have confidence in that environmental analysis or not? So we will talk about this also. But first we will start with soil, air. Well, let me show you. So right now we gonna start with this soil air partitioning coefficient and application example of equilibrium partitioning. I think I have a maximum 5 to 10 slides for this topic, and then we will go to the week 3 syllabus. Okay, so again, I have a lot of MCQs, and you people are encouraged to speak, to write in the chat box whatever the answer you think wrong or right, because I'm here to correct you. Okay, so here the first question is, in dry soil, the dominant phase in contact with soil mineral surface is, and I have four options here: water, organic carbon, air, and dissolved iron. So what do you think? What is the right answer for that? So if it is a dry soil, or if it is a wet soil, or if it is a damp soil, uh, what uh, what will be connected to that soil mineral surface? So for example, you have this soil minerals. So if it is a dry one, then what will be on this surface of the soil mineral? Either it will be water, organic carbon, air, or dissolved iron. What do you think? Hmm. Okay, so yeah, the answer will be C, that is air. So we have as I told you, we have three type of soil, and you also know about this, right? We have dry soil, we have wet soil, we have damp soil. So if we are talking about the dry soil, then these are, let's say, your soil mineral, and here there will be air. So here we will have air, mostly air. Then so this is about the dry soil, right? Then we have damp soil. In damp soil, what we will have, we have soil surface, soil mineral surface actually, and somewhat we can have water here, let's say water here or water here, and here we have air. So this will be in the damp soil condition. But if we are talking about the wet soil, so what we are assuming is that whole surface is covered with the water. So this is kind of, yeah. So and you can say, like in the lame language, you can say your all pore spaces are filled with water. This is water right now. So if all pore spaces will be filled with water, then obviously on the soil mineral surface you will have water but not air. And that's how we have three different. And why we are studying this is that if you have some contaminant, right? If you have some contaminant, the absorption capacity of your soil will not only depend on whether we have organic material in our soil or not, but it is also dependent on what what on surface we have. If we have more water, then we can assume that we can assume that the absorption by the soil will be less, because there will be some competition, right? And that's why there is important this is important to know whether our soil is dry, damp, or wet, because based on that the absorption of any contaminant will be dependent on. So that's why we are studying this. Okay, so now this is what I wanted to show you. Like we have one terminology, that is the permanent wilting point. So permanent wilting point is when you do not have any water in the pores. Here we do not have water, so you can say whenever there will be the dry soil, then you can um have this permanent wilting point, and that's how the plant will suffer, and plant will be dry also. And this is the saturation, so again you can call it as the wet soil because all the pores are filled with the water. And whenever we have some space, then we can call it as a damp soil. And yeah, so we have so on our soil mineral surface we have water connects to it, and also some air, right? And that's how the property of different type of soil based on the moisture will decide the absorption capacity of any contaminant. Okay, so now the question is, for an organic compound, let's say we have organic compound A, and here the air solid partitioning coefficient, that is K star, and this star is nothing but this is showing the equilibrium condition, right? This is equilibrium condition, will follow which order under different soil moisture condition. As I told you, how the contaminant will be absorbed by solid will be dependent on how much moisture we have on that solid, right? So if it is a soil, then how much moisture it has, based on that the partitioning coefficient will be dependent on. So we have four option here: wet, damp, dry, damp, wet, dry, dry, damp, wet. Wet is equal to damp is equal to dry. So what do you think? But before that, you have to understand what is this air solid partitioning coefficient that we are talking about. So for example, we have one compound, because it is a organic compound. So in organic compound, if I'm taking for example glucose only, C6H12O6, and here A means this is the any contaminant or any compound A. So and this 3 is nothing but 3 is representing the solid, and this one is representing the air. So this glucose, we are talking about this glucose. So where this glucose will be stayed, either at the solid or at in the air, and what will be the partitioning coefficient? So based on the organic, so if in the solid we have soil, and if soil have some moisture, if soil have some moisture, then what will happen with this air solid partitioning coefficient? Partitioning constant will be more for which of the case, dry, damp, or wet? If you are still a little confused about air solid partitioning coefficient, just let me know, I can explain it again. But this is nothing but this is the concentration. So we are referring this concentration as a rho. So concentration of A, 3 means in solid, so concentration of A in solid divide by the concentration of A, 1 means air, so in air. So this is air solid partitioning coefficient. And you need to tell me which one will have more partitioning coefficient, either it is in dry condition or is in wet condition or it is in damp condition. Any guess? Okay, Lakshmi suggested me that yeah, the dry will have more air solid partitioning coefficient. And yeah, I agree with this, but why is this case? As in the last question only, I told that if we have solid surface, this is, let's say, soil, right? And in the soil, we have, if we do have water, then this water will interfere with this contaminant A, or will have some competition with the A. And if there will be some competition with A, then obviously the absorption capacity of this soil will be reduced. So there will be less absorption in solid as comparison to air, because the solid have the surface is covered with the wet, or covered with the, let's say, moisture. So that's why this coefficient will be more for the dry condition and less for the wet condition, because in the wet condition the solid particle is bounded by the moisture, and this moisture will have some competition with the any organic compound A, and that's why C is the right answer. If there is any doubt, you can just let me know. Otherwise, we are going to the next question. Okay, there is more explanation about this. So as I already have told you, so this is solid air solid partitioning. So this is the equilibrium distribution of chemical between the air phase and the solid surface, governed by absorption to soil or particle surface. Whenever we have dry soil, it means your solid surface will be exposed, so there will be more absorption on the solid, and that's why the partitioning coefficient will be more. If it is a wet soil, then water will be coated around this solid, and that's how this option will be reduced. Okay. Why we are just studying that? The main purpose of studying is just that if we have any chemical, where this chemical we can find, either in soil or in air or in water. That's why we are studying this different type of partitioning coefficient, right? And yeah, the last part of this partitioning coefficient is all about air solid partitioning coefficient. So if it is a wet soil, the air solid partitioning coefficient, that is K star A31, is expressed as what? WA3 by SA1, WA3 by SA2 multiplied by SA2 divided by SA1. C is SA1 divided by WA3, and D is SA2 divided by WA3. And I already have told you, A is air, 2 is water, and 3 is solid. So if we want to calculate the air solid partitioning coefficient, that is Ka31, then what can be the formula for that? Any thought or any idea about what should be the formula? Here, the thing is, our soil is wet. Actually, I already have told you. If it is a not A, actually, I explain it right now. So if we have a partitioning coefficient for any organic compound or any compound A in soil and air, so 3 is solid, 1 is air. So this is something, the concentration of A in air, in 3 is solid, right? In solid, yeah, Lakshmi, this is B. So, and this is the concentration of A in air, right? But because we know that our solid is bounded by water, so what will be the formula for this? uh, A in solid divide by A in water, and then there is multiplication by rho A in water, and then rho A in air. And that's how this one is the right one. So this WA3 is nothing but this is the concentration of A in solid. SA2 is the concentration of A in water, because we know that over the solid is bounded with the water, so there will not be direct connection of solid to the air, but in between we have water because we are talking about the wet soil, right? And that's why first to the solid, then to the liquid, multiply by the liquid, and to the solid, because this need to be cancelled out, because what we need is exactly this one at last. And that's why B is the right answer. So in the wet soil, you also need to know the concentration of your contaminant A in water also. And that's how B is the right answer. Okay, the next is SA2 divided by SA1 is the derivation correspond to organic carbon partitioning, diffusion coefficient, inverse of Henry constant, Henry constant. So this is the concentration of A in water divided by concentration of A air. Yeah, so this will be the inverse of Henry law, right? So yeah, so C is the right answer, because Henry law is nothing but this is S12, right? So this is the concentration of A uh, in air divided by the concentration of A in water. And if we are going to reverse it, reverse case will be this one. So this is S21. And S21 is nothing but the inverse of Henry constant, because this is Henry constant. And that's why the C is the right answer. Okay. Now we are little advancing it. So for wet soil, the correct expression for soil air partitioning is you just need to derive it, and then only I think you can tell the right answer. But if you have gone through about this, then it may be that you have remembered the formula. So here the option A is Ka31 is equal to KOC multiplied by FOC multiplied by H, and B is Ka31 is equal to KOC multiplied by FOC divided by H. Third is Ka31 is equal to H by KOC, and D is Ka31 is equal to H. I already have got the response, that is B. Yeah, I also agree with this. This is a B, but I think I have taken the slide from actually from Sir's slide only. So this is what we learned, that if we are talking about this 3-1, right, A31, so this is nothing but the concentration of A in solid divided by concentration of A in air, right? So this is 3 and A. But because if it is a wet soil, then in the wet soil we need to divide it with the concentration of A in water, and we also need to multiply with the same, the concentration of A in water. But we already know that we already have learned this, that whenever we have 3 by 2, so solid water partitioning was Ka32, and this Ka32 was nothing but KOC and FOC. And if this is the case, and if we are putting that into this equation, then what we will get is KOC multiplied by FOC divided by H will be what we want for this solid air partitioning. So this is the uh, formula, final formula. This is just to let you know why what was FOC and what was H. And so here we already have learned about this Ka32. So 3 is solid and water coefficient. So, and because this solid have this any pollutant or any contaminant, that is A, will be attached to the organic part of the solid, and that's how this is Ma divided by MOC. So this is the mass of the organic content, and this is the mass of organic content per mass of the solid. And this is how what we are calling this MOC upon M3 is the FOC. So this is the fraction of organic carbon in the solid. So that's why this is FOC. And this part, the remaining part, will be a different one. So that's how the formula was derived, and this formula was nothing but this was the KOC FOC divided by H. Okay, so if we are increasing the soil moisture content from damp to wet, the value of Ka31 will, and I have 4 options here: increase sharply, remain constant, decrease, become independent of chemical properties. So if we are increasing the soil moisture content, so if we are making it more wet, so what will happen to the soil air partitioning coefficient, that is K star A31, whether it will increase or it will remain constant or it will reduce or it will become independent of chemical properties. So what do you think, what is the right answer for that? Yeah, so the answer should be if we are increasing the soil moisture content, then our solid air coefficient should be reduced. And as I already have talked about this, if we have any solid particle, this one is the solid particle, and uh, if we have any water around it, and this is air, then there is no direct contact of this air with the solid, but we have water in between that. And that's how the partitioning of particle of any contaminant A between solid and air will be reduced because we have in between water. So that's how D is the right answer for this. Okay, so the next question is, in the experimental determination of K star A12, the system is allowed to reach equilibrium in the closed container primarily to ensure. We have 4 options here: continuous loss of chemical A, constant temperature only, conservation of total mass of A, increase in reaction rate. So, what can be the right answer for this? So here, what condition we have? The condition we have is that we need to determine K star A12. So the K star A12 is nothing but this is the concentration of any component A in air divided by the concentration of A in water. Okay, and if we are allowing the system to reach the equilibrium, then what we will ensure at last. So this is something like this. You have water. So this is, let's say you have water, and here you have air. And let's say we are dumping something. Uh, if we are dumping any a contaminant or a component here in the water initially, and if we are allowing the system to reach to the equilibrium, and this is closed system, then what we will ensure? So we will ensure that, so this a will go to the air also. So this will be the row a1, and this will also go to the water, and this is row a2, right? And if we are dividing this will be nothing but this is ka12, that is the Henry constant. And at last what we are seeing is that whatever mass it was, let's say it was 10 kg. So, and it may be that after equilibrium we have 3 kg here and 7 kg here. So at last, what we are seeing is that wherever our contaminant A will go, but the total mass will be the same. So that's why the conservation of total mass of A will be the right answer. So this is something, wherever you are dumping the your component A, wherever it will go, but the total mass will be the same, right? So that's why we are following that conservation of total mass of A here. Otherwise the equation will be wrong. If we are saying that the total concentration will be less, then our calculation will not be the correct one. So yeah, C is the right answer. Then we have next question. If chemical A is initially present only in water, the initial mass of A in the system is. So again, this is something like this, because here the options are S node A1 V1, S node A2 V2, S star A1 V1 plus S star A2 V2, and D is K star A1 2 V2. So this is something like this, because we are talking here about the air and water, because this is A and 2. So what I'm doing is, let's say this is air and this is water, and if we are putting our chemical A into the water, then initial mass of A in the system is, right now we are not talking about the equilibrium, and that's why I got a right response from the Lakshmi, that is B, because right now if it is a mass, then this mass is nothing but this is your density multiplied by volume, right? And the density, so this is the initial mass of A. So initial mass of A will be um S naught A2, because we are putting into the water, and multiply by the volume of this water, and that's how this is the initial mass of A, but before equilibrium, and that's how B answer will be the right one. Okay, so the next question is, again we are having this mass balance, and we have partitioning coefficient, that is K star A12, that is equal to S star A1 upon S star A2. The correct expression for K star A12 is. Again, we have to have some derivation, but you may remember it. I don't know whether you just remember it or not, but yeah, we need a proper derivation to derive this K star A12. So this is this is actually very very easy to derive this. So as you already have told that if we have any contaminant A that we are putting in, let's say, water, so this will be S node A2 V2, right? We are not putting our contaminant in air but in water, and that's why the whole mass or the total mass of your contaminant will be this one, and this will be equal to uh, how much concentration you have in the water after equilibrium and how much concentration you have in the air. So this will be something that the concentration of A in water, and here it is equilibrium, right, plus the concentration of A in air and V1, and this is again equilibrium condition. And if you are equaling it, and if you are again you know the formula for this one, and if you are putting some formula into that, and then what you will get is I already have a response, that is C. Yeah, Lakshmi gave me right answer, that is the C1. So from this one, I think from this one it is very easy to derive this one. So C answer with the right. Again, I have slide from search slide only. So this is something that we have mass of A in water, and this will be equal to mass of A in water and mass of air A in air after equilibrium. This is before equilibrium. This is before equilibrium, and this is after equilibrium. And then what we are doing is just we are extracting this K star A12, and if we are moving term left to right, and this is what we will get. Okay. The next question is, again, if we have a chemical A and that is distributed between water and soil, and we need to represent the mass balance at equilibrium, then what will be the right answer? So what we are calculating is whenever you have any chemical A, and if you are moving that chemical A firstly into the water, or because this is distributed in water and soil, so there may be condition that uh, some of the part you are moving to directly to the soil, or and some part you are directly moving to the water, and you need to tell me the mass balance. So I think this is the derivation part, so I'm not taking much time for this one. So B1 is the right answer, and yeah, I think just give me yeah. So this is something that, because we have a chemical and we are putting that chemical into water and soil initially. So let's say if we are moving initially 5 kg, and let's say this is the 7 kg. So for the water, this will be the mass. For the soil, this will be the mass, right? And then after equilibrium, so there must be some equilibrium, and maybe after equilibrium the 2 kg will be here, but let's say 10 kg will be here, but at last it will be the 12 kg, right? 5 plus 7 is equal to 12, and 2 plus 10 is equal to also 12. So so initially, this is the initial concentration in water, this is the initial concentration, sorry, not concentration, this is the mass, because we are multiplying with the volume. So the mass of contaminant A, in water, mass of contaminant A in solid, and then after equilibrium, then this is the concentration, right? And so B will be the right answer. Okay, so I think this is the difficult one, and I think last one. So if we need to derive K star A32, this is again solid water, because 3 is water, sorry, 3 is solid and 2 is water. And if we need to derive K star A32 from mass balance derivation, so what will be the right answer? Again, I'm not giving much time over this question because we need to derive it, right? And we need more time to derive. So yeah, so C1 is the right answer. Yeah. So, and how we can derive this is again normal. If we know that we have initial mass of A in water, this is initial mass in water, and this is initial mass in solid, and this will be equal to whatever we have in equilibrium, as I gave you the example of 7 5, and let's say this is 2 10 after equilibrium. So this is what we are putting, and we already know about this one. WA3 by rho A2 is equal to KA32, and from here we can derive this WA3 star. And if we are putting that here in the equation, then at last what we will get is this big equation. So you need not to learn much, but I think you can derive it very easily, because if you already know all the formulas, then I think this is not difficult to derive. Okay. This is the last. Okay, so we have already talked about the concentration of A in water, concentration of sorry, A in air, in water, concentration of A in, so this is by W, concentration of A in soil or solid. And we also have talked about the partitioning coefficient. So this is Ka12, Ka21, Ka32, and Ka 2 3, right? We already have talked about this. So these are all partitioning coefficient we already have talked about. But we have new partitioning coefficient, not new, but this is well known, but different partitioning coefficient that we need to learn. This is octanol water partitioning coefficient, that is KOW, and you need to tell me the right answer for this, or you need to tell me the correct statement for this. It is the ratio of chemical concentration in air to that in soil. It determines the evaporation rate of a chemical. It is the ratio of chemical concentration in octanol to its concentration in water. It is a measure of a chemical acidity in water. And I already have got the answer C. Yeah. Yeah, this is the C answer. But again, the question is, why we are talking about octanol? It was okay if we were talking about air, water, solid water, air, soil. But what is the use of this octanol? Why we are talking about the octanol water partitioning coefficient? What is the importance for that? Any guess about this? Why we are talking about the octanol here? Why octanol is so important for us, that we can talk, then we can talk about any of the chemical. Why we are right now we were just talking about the air water partitioning, air soil partitioning, but here we have the octanol water partitioning. Why this is the case? Because octanol is very similar to human body tissues. It is very similar to the human tissue, and that's how whenever we are taking any kind of medicine, let's say. So what we can tell, how much absorption that medicine will have in the human body as comparison to the water. And that's how we can give the answer of the absorption of any kind of medicine in human body. And so that's how this octanol water partitioning coefficient is very important in pharmaceutical, pharmaceutical point of view. And that's how, yeah. So this is the chemical concentration is octanol, because octanol is similar to the human body tissue to its concentration in water. So if we are taking anything like medicine or something, so what will be the absorption capacity of human to take it? So that's how this is important for us. So yeah, C is the right answer. And this is something like how we do. So for example, this is water, and in water we have any contaminant, let's say A, or if any chemical A. If we are putting octanol, and because you know that octanol is near to the human tissue, or you can say lipid or something, and then how this contaminant A will move to octanol layer and to the water layer, and this is known as um, KOW. And because if we need to reduce the value, then we are going to calculate the log KOW. So this is the ratio of chemical concentration in octanol to its concentration in water. And from there, actually it is very important, from there we can calculate bio concentration factor, or bioaccumulation concentration factor, how much. So if it is any chemical, for example, if it is a mercury, or if it is something, any pesticide, what we were talking about, if it is any pesticide, then what is the ability of human tissue to absorb that with respect to its absorption in the water. And that's how this is very important. And because based on that, then we can calculate this bioconcentration factor. Okay. So the next question is, what does a high octanol water partitioning coefficient, if it is like K or W is more than 10,000, what it will indicate about a chemical? We have four options here. It is highly soluble in water and has low potential for bioconcentration. It is very hydrophobic and likely to bioaccumulate in organism. It is likely broken down in the aquatic environment. It is non-toxic to aquatic organism. So if you have more or high value of KOW, that is the octanol water partitioning, then what you will infer from that information? What we are indicating, if we are having the comparison of this octanol to the water as a as a carrier to any chemical A, then what we will see, if we have more value of KOW, it means more uh, pollutant A, or more the substance or chemical A will be in octanol as comparison to the water. So it means that chemical A is hated to the water, because it is not liking that water. It is hydrophobic in nature. That's why it is dissolving, or it is absorbing under octanol solution. So what we can infer from that, if we have more value of KOW, it means our chemical A is liking the octanol, is liking the human like tissue to be there as comparison to the water. So what we can say, that our chemical A is very hydrophobic, is not liking the water, and that's why KOW is more, and it is likely to bioaccumulate in the organism, because it is not liking the water. It will not be in the water, it will be dissolved, or absorbed in the human body very soon, or to any of the organism. That's why B is the right answer. Okay, the next question is, which of the following does not influence the level of bioaccumulation of the substance in an organism? The rate and mode of uptake, the ability of the organism to metabolize or eliminate the substance, the hydrophobicity of the substance and the liquid content of the organism, the molecular weight of oxygen in the environment. What will not influence the level of bioaccumulation? I already have talked about the bioaccumulation. So bioaccumulation is absorption of any chemical in organism, right? This is bioaccumulation. So we already have talked about the example of pesticide, or very famous example was DDT. DDT is getting absorbed by the human body, and this is how this is the bioaccumulation. So yeah, uh, I got answer D. Yes, so I also agree with answer D. So the molecular weight of the oxygen in the environment is not the good influencer that will influence the level of accumulation, but it will be the rate and mode of uptake, obviously. The ability of organism to metabolize or eliminate this is a substance, whether it is extracting out this or it is just accumulating in the body. And the substance hydrophobicity is the one of the important parameters that we need to know. Okay, so this was all about the partitioning coefficient. So the week one and week two content already have been covered, and right now we are moving to the week three content, that is introduction to environmental monitoring and sampling, and then environmental sampling. And whenever we are having any environmental analysis, then we need to check the quality of that analysis. So right now we will have MCQ question on these topics, and because this is not very broad topic, so we have just, I think, few MCQ question on that. Okay, a river is monitored at multiple locations along its flow. If the measured concentration of pollutant A at at the location satisfy SA2 is more than SA2 standard, this indicates that, I think this is very simple question. The river is unpolluted at that location. The pollutant is naturally occurring. Sampling error has occurred. The river is polluted at that location. What do you think? What is the right answer for that? Actually, this is very simple. If the concentration of A in water is more than the concentration of A in the water, it should. If it is a more, then yeah, it is indicating that river is polluted at that location. So this is something, because this is the concentration, right? And most of the time concentration is in mg per liter. So for example, if I'm taking the example of nitrate or something, so if I'm taking the example of nitrate, and this is I think accurate one way, not nitrate but ammonia, let's say. If it is a ammonia, or it is for ammonia, let's say the concentration is 400 mg per liter. And so this is the standard one. Let's say this is the standard one, and if you are getting 500 mg per liter, then obviously what we can say is that the river is polluted at that location, because the concentration of ammonia, or let's say nitrate, or any of the contaminant is higher than the standard concentration that we should have. So that's how the D answer will be the right one. Yeah. Okay. The next is during monitoring, pollutant concentration are found to be low upstream, increase sharply near a factory, decrease gradually downstream. This pattern suggests what? It is the diffuse, that is non-point pollution. It is a point source pollution. It is the atmospheric deposition, or it is a natural geochemical variation. We monitored something, and then we what we got is that upstream we had the low concentration, but it increased sharply near to the factory. It reduced downstream. So what kind of pattern it is? Yeah, so yeah, B answer is the right one. This is suggesting nothing, but this is suggesting the point source pollution. And you already know about what's the difference between point source and non-point source. So can you give me some example of non-point source pollution? So if it is a factory, so so let's say this is the factory and this is the river, and factory having any pipe, and that pipe is draining the water, polluted water in the river. So this is something that here pollution level was less. So this is something upstream we had the low pollutant concentration, but here we have increased, but again we will have aeration, so this will be decreased. So this is suggesting something that from factory only it is coming, and factory is nothing but this is point source pollutant, point source actually. Okay, so domestic waste is the example of non-point. Yeah, you can say this, but um, so if we have domestic waste, and if that domestic waste is actually you can say, yeah, this is non-point, but sometime if we are having the domestic waste in a very organized way, then it can be a point source at one point of time also. But I think the great example is agricultural runoff, something like that, because we do have a lot of agricultural land, and then if we are having any runoff from the agriculture, so we do not have particular pipeline from where the water is coming, and that's how I think that is also the one example along with your domestic waste. So this is something that we already have talked about. So if there is any drainage that is coming, so for example if it is coming from any wastewater treatment plant, so this is the point source. But the non-point source may be the cropland, maybe the animal feed lot, maybe from suburban urban development, maybe from rural homes. So these are the example of non-point source. I think I'm not going to the definition because you already know about this. Okay, now we are going to the biomarkers. In environmental forensics, the primary role of a chemical signature, that is the biomarker, is to measure pollutant concentration, determine toxicity level, identify the contaminant source and transport pathway, replace routine monitoring data. So, yeah, C will be the right answer, as you already have given me the C answer. So, the chemical signature, this is very important actually. So, for example, we have some company, again, let's say some pesticide company. So, this is some pesticide company, and it is draining the pollutant in a river, right? And if you want to know, and so the water is polluted, water is contaminated. So if we want to know what is the source of that contaminant and what is the transport pathway from where this contaminant came from, so that's why what we need is very important, that is the biomarker. Because we know that in pesticide, it is something you can say, any anthracene, if you have heard about this anthracene, or some particular chemicals we have from a particular company or particular industry, or you can say from the let's say from the petroleum company or petroleum industry, you will have a very particular concentration or some ratio of some chemical that will be released. And if you are able to catch that the ratio or that particular chemical or that particular ratio, then you can tell, okay, there is a high possibility that that chemical is coming from that particular industry. And then you can also tell the transport pathway also. So obviously it will tell you the pollutant concentration also, but and it will also determine the toxicity. But the main purpose in the environmental forensic is to get to know from where this is coming and what was the transport pathway. And that's why the C answer is the right one. I give you some examples. So, I have written the definition. So, biomarkers are specific chemical compound, or these may not be specific chemical compound, but this may be the pattern of compound that we are finding in water, sediments, or in any organism. So, these biomarkers are nothing but these are the fingerprint of the pollution source. So from where we can get, okay, so this is coming from that source only. And it also record the pathway the pollutant followed. So here I'm giving you the example. So for example, if the pollutant type is the petroleum, so what biomarkers we may have, this may be hopanes and sterins, and it will indicate that this is the crude oil, or there is the fuel spill. If it is a sewage, then the biomarker will be cropestanol, and so that will indicate that the human fecal contamination. And likewise, so if it is a agriculture, so pollutant type is the agriculture. If it is a coming from the agriculture, then most of the time uh, your chemical compound will be atrazine or nitrate, and you can say, okay, it is coming from the fertilizer runoff. So that's how, using that biomarker, you can identify the source and even the pathway from what path it was following, from where it came from. So this is what information we can get from biomarkers. Okay, the detection of the same pollutant fingerprint in the river water, groundwater, and a nearby industrial discharge most strongly spots liability established for the pollution source, diffuse non-point source pollution, natural background contamination, sampling bias due to seasonal effects. If we are detecting the same pollutant fingerprint in river water, in groundwater, and also from a nearby industrial discharge, so what does that mean? What strong statement you can talk about? So, not D actually. Seasonal sampling bias due to seasonal effects. No, actually, if we are having the same pollutant in same pollutant fingerprint, we are talking about the fingerprint right now. If we are having the same fingerprint in river water, in groundwater, and so what does that mean? It means that there is a particular chemical that is being, and here I'm giving you the clue that the nearby industrial discharge. No, B is again not the right answer. A is the right answer. Let me explain you why. So here what we are saying that pollutant fingerprint is from the industrial discharge. Okay, so industrial discharge also have um, some pattern of pollutant, right? So this is having some pattern of um, contaminants, let's say, and the same pattern you are identify, the same pattern of chemical or the compound you are finding in the river and you are also finding in the groundwater. So it means you have strong evidence that that particular chemical is coming from the industrial discharge only, because the fingerprint is matching. So this is something like this is the baby of that parent, because the fingerprinting is matching. So this is something, if the industrial discharge have the same fingerprint as the fingerprint we found in the river water and the groundwater, so what we can say with the confidence, we will talk about the statistical confidence later, but what we can say is we are highly confident that that particular chemical is coming from that industrial discharge. So this is not diffused non-point, this is point source, because this is coming from the industrial discharge. This is not sampling bias due to the seasonal effect. It, if it would be the seasonal effect, then there must be some variation, or it may be that river water may not have but groundwater have. So if this is the condition, then we can say there may be some sampling bias. But here, if the industrial water is having in the groundwater or in the industrial discharge have some chemical, and that chemical fingerprint we are matching in the river water and the groundwater, then we have the strong case against that particular industry, and that's why there is the liability establishment for the pollution source. So we can case against the pollution source because we do have the evidence of this fingerprint. So that's how A is the right answer. I think right now this is clear. So what we are talking about, the fingerprinting is not just same pollutant, but this is the same compound mix. This may be the same ratio, for example pH ratio you can find, the isotope ratio you can find, or same degradation pattern. So what I was saying is that fingerprinting is not just the same uh, chemical or the single chemical or single compound, but the fingerprinting may be the same compound mixture, maybe having the same ratio or same degradation pattern, and that's why this level of matching is highly specific. And if you are finding the same fingerprint in river and in groundwater, then you can say that okay, this is coming from that industry, and that's how you can case against that. So this is all about the fingerprint or the biomarkers. Okay, so the next question is, if you have particulate matter 10 and you have the time series measured outside a building that show consisting constantly higher concentration during winter month compared to the summer, the most likely reason is, and you have four option here: increased photochemical reaction in winter, reduced atmospheric mixing and lower boundary layer height, high rainfalls scavenging pollutant, and increased vegetation uptake of particles. So if you have particulate matter more in the winter as comparison to the summer, so what can be the possible reason for that? Any particular reason for that? Any guess about this? This is just the case of Delhi. In the Delhi, we have like in the winter we have uh, high concentration of particulate matter, high concentration of different gases as comparison to the summer. But why this is the case? What is the likely reason for that? Okay, so I got response from Lakshmi. That is the B. That is the reduced atmospheric mixing and lower boundary layer height. Yeah. So this is the right explanation because uh, in winter, what happen is most of the time in Delhi condition, uh, the wind speed reduces, and if the wind speed will be reduces, there will be the less diffusion, less transport of concentration of any chemical from one place to the any to the another place, and this is how it is reducing the mixing just because of the low wind speed, and that's how there will be more pollutant in the winter as comparison to the summer. I have a clip of newspaper, I think. Yeah, so there is a lot of reason why uh, we have more pollution in the winter in Delhi as comparison to the summer. The first is there is increase in humidity. If we are increasing the humidity, then this can trap particulate matter, drop in the wind speed, and this is the main reason why the atmospheric mixing is not possible, along with the inversion is the one of the most important criteria. Do you know inversion? What do you mean by this inversion? Have you heard about this term before? What do you mean by this inversion? Have you heard about this term, inversion, or the lapse rate, something like that? So the lapse rate is normally that whenever we are increasing, if we are going to the height, then temperature will be reduced, right? But in inversion, the case is inverse. If we are going to the height, the temperature will increase, and whenever we have the inversion, so this is just the lapse rate, and this condition is inversion. And if we do have inversion condition, so in that inversion condition, it is like there is no vertical dispersion of any pollutant will be trapped, pollutant will be there only, and that's how there will be no atmospheric mixing, and that's how that answer was right. That was related to the atmospheric mixing and the wind speed. Okay. Which pollutant typically shows morning and evening peak concentration that closely follow traffic rush hours? Ozone, nitric oxide, secondary sulfate, aerosol, CO2 background. So that particular pollutant is showing the peak in morning and the evening. Not C exactly, not D, something else. Okay, just see, this is in the traffic rush. Yeah, B is the yeah, B is the right answer. That is nitric oxide. So what happened is that you know that if we have traffic or if we have vehicle on the roads, again I'm telling you the example of Delhi only. So if in the Delhi we do have a lot of traffic, right? In the morning time, the traffic will release nitrogen oxide. This is in the morning time, peak time when everyone is going to the office, right? Then then we will have a huge amount of nitric oxide, but in between, in the afternoon, we will have a lot of photochemical reaction, and this photochemical reaction will reduce the NO, right? But in the evening time, again we have peak hour where the person, a lot of person will come from office to the home, and that's how again we will have the traffic rush. But here we again we do not have that photochemical reaction in the evening time, then again there will be the peak of NO. So NO is related to the traffic and when there is no sunlight, because in the sunlight NO will be reduced, and that's why this NO will be higher in the morning time and also in the evening peak. So yeah, so B is the right answer. The next question is, what about the ozone? So at what time this ozone will usually have the peak? Mid afternoon, late night due to reduced mixing, early morning during traffic peaks, and immediately after rainfall. Yeah. So, uh, can I get more response? Lakshmi told me the answer should be A. Yeah. So, as we already have talked about this, I think in week one, that ozone have the peak in mid afternoon when there is a lot of sunlight, and that's why uh, yeah, due to photochemical reaction. So again, as I told you, in the morning time NO will be increased, and if NO will be increased, then this will be converted into NO2 in the atmosphere, because NO2 is more stable. And but in mid afternoon, when we have sunlight, this will be broken down again in NO plus O, and this O will give rise to O3 whenever it is reacting with O2. So that's how this is possible just whenever we have sufficient sunlight, and that sunlight is giving you the wavelength near to near to 550 to something like 350 um nanometer. Not exactly. I think you need to check the exact wavelength that we need. But most of the time, it is the ultraviolet radiation. The peak should be in the ultraviolet radiation that can break down this NO2 to NO and O, and that's how this is possible just in mid afternoon. Okay, now we are moving slowly to the environmental sampling, and this is, I think, very simple question. In environmental sampling, concentration of a pollutant is best defined as what? Mass multiplied by volume, mass of pollutant per unit volume, volume of pollutant collected, and instrument detection limit. Chahichi gave me answer B. Yeah, you're right, because if we are talking about the concentration, so concentration is uh, it is mass by volume, right? So yeah, so whenever we are talking about, if we are doing any sampling and if we want to get uh, uh, anything, so for example, if it is NO2, if we are having the NO2 value, then it will be in the concentration. So how much mg uh, mg of NO2 we have per liter of, let's say, air. So we will measure this NO2 in the form of mg per liter, and mg per liter is nothing but it is the concentration, and that's how B is the right answer. Okay, the next question is, why is sample size an important consideration during sampling? Large volume reduce laboratory workload. Smaller volume always give higher accuracy. It determines the detection mass relative to instrument sensitivity. Sample volume has no effect on concentration. Why it is important to have a particular sample volume? Okay, so I got a C answer. from Chechi and Lakshmi. So this is it determine the detectable mass related to instrument sensitivity. And you're right, because so for example, if we have zero point 0.3 mg per liter of the concentration, if we have, and if our instrument is just measuring up to zero point 0.5 mg per liter, and if our concentration is less than this zero point 0.5 mg per liter, then it will show zero. And that's how what we have to do is we have to increase the volume of this. If we are increasing the volume, then or if we are decreasing the volume, then the concentration or the mass of that particular pollutant will change, because we are changing the volume, and that's how it will come under the reading that we can read in the instrument, and that's why it is important. I think the next slide will define it well. Yeah. So, if we are collecting the total mass, and we know that total mass is equal to concentration multiplied by volume, and this is our detection limit. So, we should have concentration concentration multiplied by volume. So, our mass should be more than the detection limit, and so this volume should be more than detection limit upon the concentration. So based on our concentration, if we know our concentration detection limit, if we know our detection limit and if we know the concentration, then we can tell, okay, this much of volume we need so that we can have a reading reading within the detection limit, right? That's why volume is very important. Okay, so the next question is, which of the following is not a primary factor in designing a sampling plan? I think this is very like stupid question. Objective of monitoring, location of sampling, number of sample, brand of analytical instrument. If we are designing a sampling plan, then which factor is not important? Okay, so I got D answer, that is the brand of analytical instrument. And yeah, we know about this, right? Because the brand doesn't matter whenever you are designing a sampling a plan. Sampling plan should be related to whatever objective we have for the monitoring, whatever location we are having, and how much sample we do need. And based on that, we can design any sampling plan. And but the brand doesn't matter. Okay, so because if we want to do the sampling, we at least should know the instrument that we can use for different type of contaminants. So, for example, our contaminant is, or the pollutant is particulate matter, that is particulate matter 10 or particulate matter 2.5. You should know what is the instrument or technique that we can use to measure the particulate matter. So we have four options here: gas chromatography, high volume air sampler, passive diffusion tube, UV visual spectrophotometer. What instrument you will use, or what technique you will use if you want to collect the particulate matter? Okay, so Chechi gave me answer B, that is the high volume air sampler. And yeah, I agree with this, because our purpose is just to collect the particulate matter. And to collect the particulate matter, we can, in a passive mode, we can collect. So, for example, if you have something like this and if the air is coming, then some of the particulate matter will be settled down. This is the one way, but in that way, uh, here we will have mass. Here we will have just mass, but we are not talking about the volume. How like how much particulate matter in what volume of air we sampled, or what is the concentration in the atmosphere. So that's why we people use high volume air sampler. So this is the instrument. So if we are sucking that air, we are sucking that air with a particular flow rate. So if we know the flow rate, we can calculate the volume, how much volume of air we are taking in, and then there will be some filter, and on the filter the particulate matter will be settled down, and that's how what we can tell is how much air pollutant we have per volume of air, because we are sucking the air with a particular flow rate, and that flow rate can give you the volume. And that kind of work can be done by high volume air sampler. I show you the picture. I think I have that picture. Yeah. So this kind of high volume air samplers we have. So we are having air inside this. Here we have filter, and then there we will have particulate matter deposit on that, and then air will be go out. And here we have some meters that can maintain the flow rate, how much at what rate we need to get the air, and in the air we have the particular matter. So this is high volume air sampler that we have to collect the particulate matter, and to tell the concentration later. Okay, because we are talking again about the sampling and monitoring or analyzing. So if we have trace organic pollutant, for example, pesticide, so what technique you will use to analyze that trace organic pollutant in the water? So you have four options: flame photometry, gravimetric analysis, pH meter, GCMS after extraction. It is a trace organic pollutant. Gravimetric is actually for mostly it is for the particulate matter, because gravity, based on the gravity, so particulate matter will be the settle under the gravity, and that's how gravimetric is mostly for the particulate matter. Or the gravimetric analysis, you can also talking about weighing something. So weighing something is not giving you the analyzing the organic pollutant. Okay, it is trace organic pollutant. Flame photometry is not for the organic pollutant. Mostly it is not for the organic pollutant. Yeah. So a D answer is the right one. That is GCMS after extraction. Uh, Gravimetric analysis is mostly to weigh something, and weighing something is not directly giving you the trace organic pollutant, because it is mixed with something else. You just need to find out, like for example, if we have soil, and in the soil we have trace organic pollutant, just weighing the soil is not giving you what organic pollutant we have and how much it is we have in the soil. So the gravimetric analysis will not work here. Flame photometry is again will not work here, because flame photometry is not for the organic pollutant. It is mostly for inorganic, or you can say the atomic structure. Whenever we have, then only that flame photometry will work. PH meter, you know that it will measure pH, and so the remaining one will be GCMS after extraction. So this is what we will use if we want to analyze trace organic pollutant. So this will be look like this. Because it is the GC, that is the gas chromatograph, and MS, this is mass spectrophotometer. So from and you know that because it is the organic, so most of like not most of the time, but many of the organic pollutant are volatile also, right? And for, if it is a volatile, if it is a organic, then the best thing is first go for that gas chromatography, because gas chromatography based on the boiling point, based on molecularity, it will separate out different organic pollutant. And after that, we are having the ion source from it, and then we are analyzing the mass. And so first what we are separating, and then we are identifying the molecular structure using mass spectrometer. So that's how GCMS is the better option if we want to analyze the trace organic pollutant. So even if you have low concentration, so GCMS can detect in nanogram and picogram. Uh, if we have complex mixture, then GC will separate that. Gas chromatography will separate that complex mixture. And to confirm the chemical, we need mass spectrophotometer or mass spectrometer, and that's how this is the best one if we want to analyze the trace organic pollutant. Okay, so the next question is, if you want to analyze the heavy metal determination in water, then what kind of instrument you will use? UV visible spectroscopy, atomic absorption spectroscopy, FTIR, gas chromatography. So here we are cancelling out this gas chromatography because this is mostly for the organic one, right? Okay, Chechi is giving me the B answer. And yeah, I also agree with this. If we have heavy metals, then we are relying on AAS, that is the atomic absorption spectroscopy. And so this is something looking like this. Uh, so whenever you have light source, then you have sample, and a sample will be chopped first, and then it will be we have atomizer that will change that into atoms. And then so the thing is, if we have heavy metals, so the good thing with the heavy metal is that it is uh, it is not making the complex with like it is rarely making the complex, so it will be present in the atomic form, or it will be present in the ionic form. And so whenever it is so whatever the wavelength it will give, it will be related to that particular element only. So that's the best thing that we have in AAS, and that's how it is beautiful to measure heavy metal in AAS. So again, I have written something. So if it is a AAS, then heavy metals are converted into free atoms, and these atoms absorb light at element specific wavelength. So this is the important thing, and this absorption will be directly proportional to the concentration. If we are talking about the UV visual spectroscopy, so this is best for the colored species or for the complex. But here we do have elemental form, mostly elemental form. If we are talking about the FTIR, then it detects the molecular vibration, and metals do not have that IR active bonds, and that's how you do not have that molecular vibration, and that's how we can't use FTIR for this. And gas chromatography, you just know that like this is for the volatile organic compound, and this will also not work. So for the heavy metal, AS will work. Okay. If you have ultraviolet visible spectrophotometry, then what you can analyze? Total dissolved solid, microbial count, nutrients like nitrate and phosphate, particulate matter size. I think the options are very easy to select the best answer out of this. Yeah, so C is the right answer. For total dissolved solid, we just need the filter and microbial count. We do not need the spectrophotometer. We have MPN. Particulate matter again is like based on the filter only. So the remaining one is the nutrient like nitrate and phosphate. So for that we can use the UV visible spectrophotometry. Okay. Now we do have two type of sampling of the water. The one is composite sampling and another one is the grab sampling. So why we are preferring that composite water sampling over grab sampling? So we have four options here. Pollutant concentration is constant. Only emergency monitoring is required. Sample volume must be minimized. Pollutant concentration varies with time. What do you think? What is the right answer? Why we are uh, preferring the composite water sampling over grab sampling? So I got response from Lakshmi, and she gave me D. Actually, D answer is the right one because you first need to understand what is the difference between graph sampling and composite sampling. So uh, water may have different concentration with different time. So what we do is we just mix some of the samples together to have the composite water sampling. And uh, grabs means random, not exactly random, Lakshmi, but this is just the one sample that we are taking, a random, or you can say randomly one sample we are taking, but composite is the mixture of all the grab sampling. So and that's why it can and that's why composite water sampling is useful because with the time pollutant concentration will vary, and that's how if we want to have the average concentration of the pollutant, then it's better to have a lot of grab sampling. Yeah, you can say the random sampling also, but grabs are the separate individual sampling, right? And if you are mixing that grab sampling, then we'll have the composite water sampling. So here also you can see something like this. So graph sampling, and then you have different graph sampling, separate sampling, random sampling, you can also say. So this is something, the separate sampling you have at the different time, but if you are mixing it, then it will be the composite sampling. And the advantage of it is that because we can have the average concentration of pollutant in the water. So that's how this composite having the benefit over grab sampling. Okay, now we are moving to the detection limit of an analytical technique. So what is that detection limit? Maximum measurable concentration, instrument precision, lowest concentration reliably distinguished from zero, sampling duration. Let me see what I got. Yeah. So detection limit is actually the lowest concentration. So this is something, if you have any weighing machine. So if you have any weighing machine and if you are measuring something, and for example, if you have this is 0.0000 gram of something you have, but your measuring machine having just 0, and then it is measuring 0.1 gram, 0.2 gram. So this is something that either it is measuring up to zero point 0.1. Otherwise, if there is something, the concentration or the mass of your pollutant or of any chemical is less than zero point 0.1, then it will show just zero. So if you have like the mass, if it is 0.000 1 gram, then it will be shown as zero only, because the lowest limit uh, to measure for any for this instrument is zero point 0.1. So this is something, this is the lowest concentration that we can distinguish from zero. So we can tell the difference between 0 and zero point 0.1, because 0 is nothing, but zero point 0.1 is something that we have. But if we have the concentration less than zero point 0.1, then it will be shown as the zero only. So the detection limit is something that is the lowest concentration that we can differentiate it from the zero value. So that's how the C answer is the right one. Okay. In the gravimetric determination of total suspended solid, the mass of suspended solid is calculated as mf node minus mf1, mf1 plus mf node, mf1 minus mf node, mf node divided by mf1. Okay, so I got C from Chechi, that is mf1 minus mf naught. So this is mass of empty filter paper. And okay, so what we are doing is, yeah, initially we have filter paper, we are just weighing it. So for example, the filter paper weight is mf naught, but we will have some particulate matter on this, or the suspended solid, then the mass will be mf1. So if we are subtracting, then we will get the total suspended solid. So this is the easiest one, but yeah, so C is the right answer. Okay, so uh, if my mf node is equal to mf1, so what conclusion I can have? TSS is below the detection limit of the method. Filtration was unsuccessful. TS is exactly zero in the water. All suspended solid passed through the filter. Mm, D, not D. Yeah, you're writing something. Not D. All suspended solid pass to the filter. Okay, so the thing is, there may be multiple answer of this, but I think the most appropriate conclusion I'm getting, I want to get. Yeah, so A is the right answer actually. Yeah, because after filtration or before filtration, we know that air is not very clean. We will have some suspended solid in the air or in the water, no matter what fine condition we have. But if it is equal to zero, it means there is a something wrong with it, right? So it may be like the filtration was unsuccessful, it may be, but the most appropriate is that our weighing machine or our gravimetric analysis is not able to calculate that minimum amount that we have of that total suspended solid, because the detection limit is lower than that. uh, this is not real, because most of the time we will have some TSS. It can't be zero. All suspended solid passed through the filter. So here we have some problem with the filter also, but I think most appropriate will be that we have some problem with the detection limit only. So A is the right answer. Okay. So we have gravimetric method that has a detection limit of 1 mg of solid. If a 1 liter water sample contain total suspended solid is equal to 0.3 mg per liter, the correct report is TSS is equal to 0.3 mg per liter. TSS is equal to 0 mg per liter. TSS is less than detection limit. TSS is equal to 1 mg per liter. Yeah. So C answer will be the right one because um, detection limit is 1, and if we are getting like TS less than 1, then it means it will give us the 0 value, but 0 is not the right value. So what we can comment on it is that TSS is less than the detection limit. Yeah, so C is the right answer. Uh, to reliably measure a low TSS concentration when the detection limit is fixed, the most effective approach is to, we already have discussed about this, but I think you can give the answer it very quickly. Use a coarser filter paper, increase the sample volume filtered, reduce filtration time, dry the filter at lower temperature. Yeah, Cheshi gave me answer B, that is increase the sample volume filtered. Yeah, we already have discussed about this. If we are increasing the sample volume, then the concentration will be increased, and so mass will be increased. And if mass is increasing, then obviously it will go above the detection limit, and we can detect it, right? So that's how we can increase the sample volume. If the detection limit is like we can our mass can be our mass will be more than the detection limit if we are increasing the volume. So this is something we already have learned, right? Okay, if method has the detection limit of 1 mg, and if expected TS is equal to 0.3 mg per liter, the minimum sample volume required to exceed the detection limit is closest to 1 liter, 2 liter, 3 liter, 4 liter. Using that formula, I think that you can calculate. Not 2 liter, something else. It is something like this. Not 3, not 3, not C. So this is something like that. 1 liter volume having zero point 0.3 mg, right? 2 liter volume will have zero point 0.6 mg, right? 3 liter of water will have zero point 0.9 mg per mg, right, of total suspended solid. But because our detection limit is 1 mg, and this zero point 0.3, zero point 0.6, zero point 0.9 are still less than 0.1, less than 1 mg, still we can't detect it even if our volume is 3 liter. So we should have 4 liter of volume. That's how it will be 1.2 mg, and this 1.2 mg we can measure because this is more than 1 mg. So closest is 3 liter, no doubt, but we can't detect it, right? But for the detection, we have to increase the volume. And that's how we are going to the 4 liter, not to the 3 liter, because if we, even if we are increasing to the 3 liter, we are not able to detect the exact mass, right? So not B, not C, but the answer should be D, right? Okay. In instrument analysis, a signal is considered reliable detectable when signal is mostly equal to noise, signal is more than the noise, signal is less than the noise, signal is more than noise, noise remain constant with time. we know that, right? The signal should be more than noise. So for example, if like if this is just the noise that we have, and if our signal is something like this, then from like if it is a more than the noise, then the signal will be considered reliably detectable, right? So C answer will be the right one. Yeah. Uh, uh, we have one method that is or one limit, that is MDL, that is the method detection limit, that represent what? The concentration at which signal equal to noise, the minimum concentration that can be distinguished from the blank with statistical confidence, the lowest concentration that give zero noise, the average of blank measurement. Not D actually. Yeah, B is the right answer. So this is the minimum concentration that we can differentiate from the blank with statistical confidence. So, so this is known as the method detection limit. So B is the right answer. Okay, according to standard practice, MTL is often estimated as the mean of blank signal, 2 multiplied by standard deviation of analyte signal, 3 multiplied by standard deviation of blank measurement, and maximum observed noise. I already got response from Chaichi, that is C. Yeah. So for the standard practice, MDL should be estimated as 3 multiplied by standard deviation of blank measurement. And here the blank measurement, the number of sampling should be uh, equal to 7. Okay, so now we are moving to the accuracy and precision. So how you can differentiate the precision from the accuracy? So precision measure closeness to the true value, accuracy measure repeatably, precision reflect repeatability, accuracy reflect closeness to the true value. Both means the same in environmental measurement. Chechi gave me C. Yeah. So we have two term, that is precision and accuracy. So accuracy means closeness to the true value, and true value we can get from the standard. Precision is repeatively. So if we are repeating the analysis, either it is giving the same value or not. So this is something about the precision. So the C answer is the right one. Okay, so if we are using the true value in the accuracy, so what do you mean by this true value? The highest measured concentration, a value obtained from a reference standard or accepted method, the average of repeated measurements, the value measured with the highest sample volume. So Lakshmi gave me a B answer, that is a value obtained from standard method or accepted method. Yeah. So true value is like if we have some standard or if we have some accepted method, and from where what we will get the value, so that will be considered as the true value, and then we will compare our value with the true value. If it is near or if it is equal to true value, then we can say that we have the accuracy of like 100%, or based on like how it is differing from that true value, we can also tell with what confidence the accuracy is what and what. So this is how we can compare our data with the true value, and then we will get some accuracy. But again we need to do some statistical tests so that we can tell the accuracy probability. So so for example, if it is a we are how much sure we are, if we are saying that we like the accuracy is 90%, so we have to tell the confidence level also. Yeah. So in gravimetric analysis, an unknown sample mass is compared against a 5-gram standard. This process primarily helps to improve detection limit, increase precision, establish accuracy through calibration, reduce environmental variability. So yeah, uh, answer will be C, because if we are comparing it with the standard or the true value, then the case will be accuracy but not the precision, but not the detection limit or something else. So yeah, answer will be C only. Yes. If we have a calibration plot of instrument response versus mass or the concentration, uh, then this plot is primarily used to improve precision by reducing noise, determine the detection limit, convert instrument response into an unknown concentration, eliminate systematic error automatically. So I, not the detection limit, Lakshmi. I think, yeah. Let me tell you. If we have, this is our instrument response. What is mass? And let's say if we have something like this, so what it will be? Not A. This will be C actually. That we are converting instrument response into an unknown concentration. So this is something you just need to see. Like for example, if it is a um, if it is how can I say this, for example, if some instrument is based on pressure difference or some based on voltage difference, so on the y-axis you have instrument response, and instrument response may be maybe voltage difference or maybe pressure difference, um, and if this difference is measuring the mass. Okay, so if we do have linear relationship of this, let's say the voltage difference with the mass, and if we know that if we will have that particular voltage difference, then the mass will be this, and if we have particular voltage difference, then the mass will be this, and then we will have the linear relationship. So if we just know the a difference, then we can tell what will be the mass of that unknown unknown chemical, what will be the concentration or mass of that unknown, right? So that's how C is the right answer actually. I think this is like, I don't know I'm able to make you understand or not, but this is how like this is useful for this one primarily. Okay. Uh, I think we gonna have one or two more questions, and we will go for the dinner. Yeah. So an unknown sample lies outside the linear calibration range. The best analytical practice is to extrapolate using the same calibration line, ignore the result, dilute the sample to bring it within the linear range, increase sample volume. I think you are confused with C or D, I think. Yeah, so I got C and D. Yeah, but C is the right answer actually. Because if we gonna dilute the sample, so that's how we will go within that linear range. So no doubt, the sample, if we are increasing the sample volume, this is also the dilution only. So you can say C and D both can be right, but if we are accurately, if you want the answer, then C is the more accurate answer. Okay, so if we have a slope of the calibration between time t1 and time t2, and t2 time is after 5 days, and even if if you have r square value that is remain high 0.80, then what is the most correct interpretation? The calibration is valid because R is high, the instrument precision has improved, the instrument response has drifted with time, affecting accuracy. The analytical method is no more sensitive. Not A. As I told you, the calibration slope is changing. So again, I'm giving you the example: the difference in the volume, the difference in voltage versus the concentration, right? Concentration or mass. We should have that proper slope, right? If we are having different slope line, then after some time, so different slope line, it means your voltage difference is not giving the same concentration. So with the time, it has been shifted. So and there may be two line, and two line, each line may have, because the calibration and the mass, if we are having the coefficient, regression coefficient or r square something, it can be high in both cases. But the thing is, it has shifted, the line should be the same. So it means over the time the instrument response has been drifted, and we need the accuracy check again, right? So C is the right answer. So I think we have two or three question, then we can like solve that in week 4. And yeah, so I think I need to stop here because the time is up. So thank you so much. We will solve more question on week 4, and you people are welcome to attend that week 4 session on Tuesday from 6 to 8. And thank you so much. Thank you so much. And I think this is the time you can go up.
Thank
So
you, Guru.
yeah, thank you, Apurva. Thank you, Lakshmi. Thank you, JJ. Okay.